Hi, welcome to Math Fun. Today we are going to talk about e, which is the base of natural log. It's probably one of the most important and most famous constants in mathematics. Some people like to call e the Euler constants, but like many other ones, I would rather call gamma as the Euler constants. So as a matter of fact, I have another video about gamma in my channel, and I have put the link in the description of this video for you. You may want to check it out. So E is the base of the natural log, and we all know E equal to 2.71a2a and continue. It's a irrational numbers. It's in fact a transcendental numbers. If you are not familiar with what transcendental numbers are, I would suggest you check out my other videos, and I also have the link in the descriptions. Now, typically, E is expressed as the limit of this when n go to infinity. 1 plus the reciprocal n and the sum of that to the power of n. Or some people would like to express E equal to the limit, and again n tend to positive 0 obviously. And here is 1 plus the reciprocal of 1 factorial plus the reciprocal of 2 factorial plus that, and then go to the reciprocal of n factorial. So these are two expressions. So today we are going to show that these two expressions are in fact equivalent to each other, and then we are going to show that the limits actually exist. At the same time, we're going to prove that E is a irrational number. Now, it's out of the scope of this video to show that E is a transcendental number. That is much more difficult. So let's get started. We will start by having these two series, we call it En and S sub n, okay? Just to the power of n, or this is the sum up to n, and there's no limits. For now, we do not know whether there are limits or not, isn't it? So let's go with the second one first, Sn first. Now, Sn plus 1 minus Sn, obviously, because the first n plus 1 item are the same, isn't it? Equal to n plus 1 factorial reciprocal, and this is obviously bigger than 0. So what that means is that the series S is increasing monotonely, okay? At the same time, let's look at Sn. Sn equal to 1 plus, well, the factorial 1 is 1 plus factorial 2 is 2 times 1 plus, let's have a couple more. Factorial 3 is 3 times 2 times 1 and the reciprocal that plus factorial 4 is 4 times 3 times 2 and then times 1 and factorial, and then we're going to dot plus, okay, I'm not going to write down n factorial, you know what that is. So now this is obviously smaller than 1 plus 1 plus a half. Well, all those are equal, but this one we are going to make it 2 squared. reciprocal. So 3 is bigger than 2, and 2 is 2. Obviously, this is true. And yes, we're going to make this one as 2q reciprocal plus dot 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 plus. We're going to have 2 to the power n reciprocal, isn't it? Now, this whole expression is equal to 1 plus 1 plus, well, as you can see, in fact, let's make it smaller instead of equal. The first item is a half, and over what? Over 1 minus a half, isn't it? And this will be 1. That equal to 3. So that tells you that no matter how many items you have in Sn, Sn is always smaller than 3. In other words, Sn is bounded above. So it's increasing but bounded above. Well, that tells you Sn has a limit. Okay, has a limit. So we finished the first part. We proved that Sn has a limit, but we have not proved that En has a limit. So let's do the next step. Next, we are going to prove that En's also monotone increase. So how can we do it? It's very simple, but it's quite elegant as a matter of fact. So we're going to have 1 plus the reciprocal n to the power of n, which is exactly En, but we're going to take the n plus 1 root. And we can write it down as this 1. So we take 1 actually here, get an extra 1, but it's 1. So times what? Times 1 plus the reciprocal n, and have another 1 plus the reciprocal n. And how many do we have? We have a total of n, isn't it? 1 plus the reciprocal n. And the whole thing, we're going to take the n plus 1's root. And as you can see, this is a geometric means of that n plus 1 number. And they are not the same, by the way, because 1 is obviously not equal to 1 plus the reciprocal n. So that means this is smaller than their arithmetic mean. So how do you calculate arithmetic mean? Well, you have n plus 1 here, and then you have n plus 1. You have a total n. You have n item here, don't you? So over here we have a total n times 1 plus the reciprocal n, and now you see it. This will give you n, that will give you 1, so that means it will be n plus 1. You have a n plus 1 and then plus 1, isn't that true? Okay, so that will give you 1 plus n plus 1 reciprocal. Now what? Well, remember we have a n plus 1's root out here, so we just express it out. That means 1 plus the reciprocal n and the sum to the power of n's smaller, isn't it? Smaller than 1 plus the reciprocal n plus 1 and the sum to the power of n plus 1. And this is En, isn't that true? This is En plus 1. Okay, so En's also monotone increase. So we get the first step. Now let's do the next step. Now let's do a binomial expansion of En. So En, and we're going to expand that equal to the first item is obviously 1. The second item will be N divided by factorial of 1, which is 1, and times reciprocal of N plus N times N minus 1 divided by 2 factorial times N square reciprocal plus and let's do it to M. So that will equal to N times N minus 1 times to N minus M plus 1. Open our space here, but that's okay. Divided by M factorial. And then we don't have space to write, so I'm going to write here M to the power of M reciprocal, right? So, and then we'll continue. Now what do we see here? We can compare the items of En and Sn. The first item is the same. The second item is actually the same because you can cancel out the N. The third item, this part is the same. However, though, N times N minus 1 divided by N squared is smaller than 1. So in other words, this item is bigger. And in fact, all the items along the way are bigger because, for example, this one on Sn, it will be N factorial reciprocal, but you will multiply by these portions. This portion is again smaller than 1, isn't it? So that means En is in fact smaller than Sn. And we just proved that Sn is smaller than 3. Okay? At the same time, we also proved just now that En's increase monotonely. So that tells you En has a limit too. So En's limits exist. And because En is smaller than Sn, what that tells you though is limit of En will be smaller or equal to limit of Sn. And let's call the limit of Sn S, and we're going to call the limit of En E actually. Okay, so that is one thing we find out, that E is smaller or equal to S. Now, this time we are going to again expand En, but we're just going to write the first M plus 1 items. Okay, so our M here is smaller than N. So obviously En is bigger than the truncation portions of itself because all the items are positive. And now what? Now we will fix M. So let M stay the same all the way, but let N go to infinity. Then this expression will equal to, so the expression above will equal to 1 plus 1 factorial reciprocal. This one cancel out, isn't it? Plus, when your N go to infinity, this one will be 1 now, right? It tends to 1, approach to 1, so that will be 1 divided by 2 factorial plus plus 1 divided by m factorial. And this number obviously equal to s m. Isn't that true? And now what? Now we let m go to infinity. So just now we let n go to infinity and fix m. We got this expression. Now we let m go to infinity. Now what that means, what? When this one go to infinity, then you get s, right? The limit of s, and we just proved that. That get you the limit of s. Isn't that true? Now we let m go to infinity. Well, this is the limit of en, isn't it? And that will give you e. So in other words, in this way, we're actually going to show that e is bigger or equal to s, because em is bigger than sm, and now we let it go to infinity for both that go to the limit, and we already proved that that limit exists. So this is the case, but we just proved that e is smaller or equal to s, and now e is bigger than or equal to s. That means there's no choice. E equal to s. In other words, we just proved that these two expressions equivalent to each other. Their limit exists. Obviously, their limit will be the same. Now, let's prove that E is irrational. Okay, remember we just proved that E equal to 1 plus factorial 1 reciprocal plus reciprocal 2 factorial plus continue plus, let's call it b factorial plus b plus 1 factorial reciprocal and plus continue to infinity, isn't it? So we will prove by contradictions. We're going to let E equal to A over B, and A and B are both natural number, and we're going to choose A and B in the way that they don't share any factor, as a matter of fact. Okay, so then what? Well, that means A over B equal to the expression we have over there, right? 1 plus 1 factorial reciprocal plus 2 factorial reciprocal plus, I already have the item out there, b factorial reciprocal, and then we have a b plus 1 factorial reciprocal and continue. And on both sides, we're going to multiply b factorial. So on this side, you're going to have a times b factorial divided by b equal to, this will be b factorial plus b factorial divided by 1 factorial plus b factorial divided by 2 factorial plus continue until b factorial divided by b factorial, and then you plus b factorial divided by b plus 1 factorial, and of course you have a b factorial divided by b plus 2 factorial easily, and we can continue. Now we can see here b factorial, we all know, equal to b times b minus 1 times b minus 2, but I'm not going to write it down, times until 3 times 2 times 1, isn't it? Right? So b factorial, you have a factor of b, you can cancel it out. So that means this is a integer, because a is also integer. There, a and b are both natural number. This is an integer, this is an integer, this is an integer, because you have a factor of 2 in b factorial, and continue. All those are integer, all those are integer up to this point. Now what is this one equal to? So let's call that portion from here, let's call it delta. Okay, delta obviously equal to 1. Remember, b plus 1 factorial will equal to b plus 1 times b factorial, isn't it? So that would be 1 over b plus 1 plus 1 over, now b plus 2 factorial equal to b plus 2 times b plus 1 and then times b factorial. Isn't that true? So that would leave you with b plus 2 times b plus 1. And you can continue. Now the whole thing will be smaller than b plus 1 here. We're going to replace anything bigger than b plus 1 as b plus 1. So that's why you have a smaller size out here. So this will be 1 over b plus 1 square, and b is obviously bigger than 1, isn't it? And continue, right? Now this whole thing equal to what? Well, it equal to, the first item is b plus 1, isn't it? And then we will do 1 minus this one. That will equal to 1 over b. You can do it yourself, it's very easy. Okay? And we know b is bigger than 1, or even it is 1, it doesn't matter because you have a smaller sign out there. This is not smaller or equal to. Okay, I just want to mention the fact that we have a smaller sign out here. So this, even if this b is 1, it doesn't matter. This is smaller or equal to 1. So in other words, the delta portions is smaller than 1, and definitely delta is bigger than 0, isn't it? Right? So the delta is bigger than 0 and smaller than 1. In other words, it could not be an integer. However, this is an integer, as we said just now. This portion is an integer, so you will have this problem. An integer equal to a different integers plus a non-integer, a number that is between 1 and 0, and that cannot be possible. So we have a contradictions that tell you that e could not be a rational number. So that means e is irrational, and this is how you prove it. I hope you like these videos. It's quite a lot to digest, isn't it? But from the beginning to the end. we show two expressions of E. We show that they are in fact equivalent to each other. We show that their limits exist. And the limits we call E. And finally, we prove that E is irrational. So I hope you enjoy these videos. Please make sure you like and subscribe, and I will see you in the next videos. Bye bye.